Life is full of complex problems, whether it's finding the quickest route to work, making the most of a limited budget, or even just deciding what to have for dinner. We're constantly faced with decisions that can feel overwhelming. Often, the best way to tackle these challenges is to break them down into smaller, more manageable pieces. This approach, known as problem decomposition, lies at the heart of many problem-solving strategies, and it's a fundamental principle behind a powerful algorithmic technique called dynamic programming. Dynamic programming is like a master chef with a secret ingredient. Just as a chef can transform simple ingredients into a culinary masterpiece, dynamic programming can take a complex problem and break it down into smaller, overlapping sub-problems. By solving these sub-problems just once and remembering their solutions, dynamic programming avoids redundant computations, saving time and resources. This elegant approach has revolutionized the way we solve a wide range of problems, from finding the shortest path in a network to optimizing investment strategies. In this exploration of dynamic programming, we'll embark on a journey to demystify this powerful technique. We'll start with a clear and concise definition, using relatable examples to illustrate its core concepts. Then we'll delve into the step-by-step process of applying dynamic programming, unraveling its elegance through practical scenarios. Imagine you're planning a road trip. You have a map, your starting point, and your desired destination. There are many possible routes you could take, each with its own distance and estimated travel time. Your goal is to find the fastest route, even if it means considering different highways, back roads, and rest stops along the way. This is where dynamic programming comes in. Dynamic programming is an algorithmic technique that solves complex problems by breaking them down into smaller, overlapping subproblems. It then solves each subproblem just once, storing the solution in a table or a similar data structure. When the same subproblem is encountered again, the algorithm simply looks up the pre-computed solution, avoiding redundant computations. This divide and conquer strategy, combined with the clever use of memoization, storing and reusing previous results, makes dynamic programming incredibly efficient for solving a wide range of problems. Whether you're a computer scientist optimizing algorithms, a financial analyst maximizing returns, or simply someone trying to find the quickest way home, dynamic programming provides a powerful framework for tackling complex challenges. Dynamic programming might sound like a complicated computer science concept, but it's surprisingly relevant to our everyday lives. Let's say you're at a vending machine and you want to buy a snack that costs $1.75. You have a pocket full of quarters, dimes, and nickels. How many different combinations of coins can you use to make the exact change? This problem, though seemingly simple, can be solved efficiently using dynamic programming. Instead of trying to enumerate all possible combinations from scratch each time, we can break it down. We start by figuring out how many ways we can make change for smaller amounts, like 5 cents, 10 cents, and so on. Then we use these solutions to build up to our target amount of $1.75. This is just one example of how dynamic programming manifests in everyday situations. From calculating the best way to pack your luggage to finding the shortest path on a map, dynamic programming is quietly working behind the scenes, optimizing our decisions and making our lives a little bit easier. To truly grasp the power of dynamic programming, let's break down its application with a simple example, calculating the Fibonacci sequence. This famous sequence starts with 0 and 1, and each subsequent number is the sum of the two preceding ones, 0, 1, 1, 2, 3, 5, 8, 13, and so on. The naive approach to calculating the nth Fibonacci number involves recursively calculating the n1 th and n2 th numbers. However, this method leads to a lot of redundant calculations. This is where dynamic programming shines. With dynamic programming, we solve this problem bottom up. We start by storing the Fibonacci numbers for 0 and 1, which are 0 and 1 respectively. Then we iterate through the sequence, calculating each subsequent number by adding the previous two and storing the result. This way, we only calculate each Fibonacci number once, saving a significant amount of computation time, especially for larger values of n. Section 5, Climbing Stairs, Applying Dynamic Programming. Imagine you're climbing a staircase. You can take either 1 or 2 steps at a time. How many distinct ways can you climb to the top, say the nth step? This problem, often dubbed the climbing stairs problem, is a classic example of how dynamic programming can be applied. Let's say you want to reach the 4th step. You can get there in the following ways. 1, taking 1 step, then another, 1 step, then another 1 step, and finally one more 1 step. 2, taking 1 step, then another 1 step, and then a final 2 steps. 3, taking 1 step, then a 2 step, and then a 1 step. 4, taking 2 steps, then another 2 steps. 5, taking 2 steps, then 2 1 steps. That's a total of 5 distinct ways to climb to the 4th step. Now imagine trying to calculate this for a staircase with 100 steps. It would be incredibly tedious to manually enumerate every possible combination of steps. Dynamic programming provides an elegant solution. We can break down this problem by considering the number of ways to reach each step leading up to the nth step. For instance, there's only 1 way to reach the 1st step. Take 1 step. There are 2 ways to reach the 2nd step. Take 2 1 steps or 1 2 step. To reach the 3rd step, you can either take 1 step from the 2nd step or 2 steps from the 1st step. Notice a pattern here. The number of ways to reach the current step is simply the sum of the number of ways to reach the previous 2 steps. We can use this relationship to build our solution from the bottom up. Section 6. Delving into the past. The history of dynamic programming. The roots of dynamic programming can be traced back to the 1940s and the work of Richard Bellman, an American mathematician at the Rand Corporation. At the time, Bellman was tackling optimization problems related to multi-stage decision processes, particularly in the context of resource allocation and engineering control systems. Bellman recognized that many complex problems could be broken down into smaller, overlapping subproblems. He developed the concept of dynamic programming as a systematic approach to solving these problems by recursively breaking them down, solving the subproblems, and storing the solutions to avoid redundant computations. The term dynamic programming itself has an interesting history. Bellman chose this name during a time when the field of computer science was still in its infancy, and the term programming didn't carry the same connotation it does today. In Bellman's words, dynamic programming was chosen to be intentionally vague and to avoid any negative connotations associated with the word research at the time. He wanted a term that would sound impressive and wouldn't raise eyebrows among his funders, who were often skeptical of mathematical research. Despite its somewhat obscure origins, the term stuck, and dynamic programming quickly gained recognition as a powerful problem-solving technique. It found applications in a wide range of fields, from operations research and economics to control theory and computer science. Section 7. Dynamic programming in the modern world. Today, dynamic programming is an indispensable tool in countless applications across various disciplines. Let's explore some of its notable modern uses. Computer science. Dynamic programming is fundamental to algorithm design, particularly in areas like string algorithms, graph algorithms, and computational biology. It's used in applications like sequence alignment, finding similarities between DNA sequences, text justification, optimally arranging text in paragraphs, and image compression, reducing the size of image files without significant loss of quality. Operations research and finance. In the realm of optimization, dynamic programming plays a key role in solving problems related to resource allocation, inventory management, and financial modeling. It's used by businesses to make strategic decisions such as optimizing production schedules, managing supply chains, and pricing options. Artificial intelligence and machine learning. Dynamic programming is a cornerstone of reinforcement learning, a type of machine learning where an agent learns to make decisions by interacting with an environment. It's used in applications like robotics, game playing, think Deep Blue, defeating chess grandmaster Garry Kasparov, and autonomous vehicles. Bioinformatics. Dynamic programming is crucial for analyzing biological data, such as DNA sequences and protein structures. It's used in applications like gene prediction, identifying genes within DNA sequences, protein folding, predicting the three-dimensional structure of proteins, and drug discovery, designing new drugs based on molecular interactions. These are just a few examples of how dynamic programming is shaping our world. As technology continues to advance, we can expect even more innovative applications of this powerful technique in the years to come. Section 8. Beyond the Horizon, the future of dynamic programming. The future of dynamic programming is bright, with ongoing research and development pushing the boundaries of its capabilities. Here are some exciting areas where we can expect to see significant advancements. Approximate dynamic programming. As problems become increasingly complex, finding exact solutions using dynamic programming can become computationally expensive. Approximate dynamic programming techniques aim to address this challenge by finding near-optimal solutions with reduced computational requirements. Quantum dynamic programming. With the rise of quantum computing, researchers are exploring how to leverage the principles of quantum mechanics to develop even more powerful dynamic programming algorithms. Quantum dynamic programming has the potential to revolutionize fields like drug discovery, materials science, and artificial intelligence. Dynamic programming for big data. The explosion of data in recent years has created new challenges and opportunities for dynamic programming. Researchers are developing scalable dynamic programming algorithms that can handle massive datasets efficiently. Dynamic programming in edge computing. As edge computing gains traction, there's a growing need for efficient algorithms that can run on devices with limited resources. Dynamic programming, with its ability to break down problems and reuse solutions, is well suited for edge computing applications such as real-time decision-making in autonomous systems and personalized recommendations on mobile devices. These are just a glimpse into the exciting future of dynamic programming. As technology evolves and new challenges arise, we can expect dynamic programming to continue playing a pivotal role in shaping our world. Section 9. Conclusion. Embracing the elegance of dynamic programming. Dynamic programming, with its elegant approach to problem solving, has become an indispensable tool in our modern world. From optimizing algorithms to making strategic business decisions, its impact is felt across countless domains. By breaking down complex problems into smaller, overlapping subproblems and storing the solutions, dynamic programming unlocks efficiency and scalability that wouldn't be possible with brute force methods. As we've explored its applications in various fields, from computer science and finance to bioinformatics and artificial intelligence, it's clear that dynamic programming is not just a theoretical concept confined to textbooks. It's a practical and powerful technique that's shaping the way we solve problems and make decisions every day. As technology continues to evolve, we can expect dynamic programming to play an even more prominent role in our lives. With ongoing research and development pushing its boundaries, dynamic programming is poised to unlock new possibilities and drive innovation across various industries. By embracing its elegance and understanding its underlying principles, we can harness the power of dynamic programming to tackle the challenges of today and tomorrow.